In this homework, we're going to be using regular expressions to extract the data that we want from a large text file, which in this case will be the material properties sheet for different common chemicals. So what we first want to do is import the packages that we're going to use. So we're going to use the NumPy for when we're performing calculations with our extracted values. So for example, when we're calculating the vapor pressure and heat or vaporization of materials using extracted coefficients. We're also going to want the string Python library, which we'll use for modifying the names of our coefficients when we extract those from our file. We're going to need the regional expression or regular expressions Python library, which is what we're going to use to extract the data that we want from our text file. And we'll need the requests Python library, and we're going to use requests for downloading the file that we want to be extracting from into Python. We're also going to install the .map Python library, and from this we're going to import specifically the .map class, and a class in Python is used, or a class is used for creating objects in Python. So in this case, what the .map class does is it will take our dictionary that we create using the regional expressions, then we'll have a dot and then specifically the property for that material that we want to look at. Map Python library, and from this we're going to import specifically the .map class, and a class in Python is used, or a class is used for creating objects in Python. So in this case, what the .map class does is it will take our dictionary that we create using the regional expressions, then we'll have a dot and then specifically the property for that material that we want to look at. So once we have our packages imported, we're going to want to download the file that we're going to be looking at into Python. So for example, I have pulled up the raw data for the properties of water, and here's the URL that we need to copy. So the full URL that we're going to be looking at is this, but we are going to want to be able to easily change the URL that we're looking at so that we can look at the properties of different materials. So we have all of these materials here, and they follow the same file path. The only difference is that for each material, there's this name of the material once we get inside this data folder. So what we want to do is specify our base URL, which will be everything before we get to the name of the material. And we have the component that we're going to be looking at, which in this case is water, and then the suffix of this URL, which is just props.txt. Now, we're going to use the requests library to download this file, and we're going to do that using the get function inside of the requests library. So we'll create a variable called text request in the get function. Inside the get function is where we put our URL, so it'll be using these 3 strings that we created. It'll be the base URL plus the component plus the suffix, and we want this to be the formatting of this to be a text file. Okay, so now we have our entire text file here for water. We could also change the material. So for example, we could specify we want the component to be methanol instead, and now we would get the materials for methanol, or the properties of methanol. So once we have our file downloaded, we need to create a regular expression, which will create a pattern that we can use for looking through our data file in order to pull out the data that we actually want to work with. So what we're going to do is go to Regex 101. I've already copied and pasted the text file for water in here. And we've got 2 groups that we're going to want to capture so that we can put them into a dictionary. So the first is the title of the property that we want to look at, and the second is the value of that property. For this section, or for this particular regular expression, we're only going to be creating a pattern for values that have one static value. So all of these values. We'll have to create a second pattern for the values that contain different coefficients that get put into an equation. So for the first pattern, we're going to be using the multi-line regex flag, which means that we're going to specify pattern matches the beginning of each line of code, and we're going to use a caret to specify our pattern starts at the beginning of a new line. We'll use a $sign to specify that our line ends at the end of each line of this text file. So we can see that before we get to any of the groups that we need to capture, there's a space at the beginning of each line, so we don't want to capture that. The first group that we want to capture is the title of the property that we're looking at. So this will include any uppercase or lowercase letters, so we'll use the /W to symbolize all of those characters. There's also spaces in here that we'll want to capture. Some of these titles also include a dot that we'll want to include, as well as the division sign. And this one, specific gravity, also has numbers, so we want to include numbers. So starting out, it only is going to capture one value. We want to specify that it'll capture one or more values, so that way we can get the whole name. But we don't want all of these spaces in between the title of the property we want and the actual value. So we'll want to use a lazy capture for that. So it doesn't look like it did anything yet, but what we'll see is that after this value, we want a space, and we're going to want one or more values of that space before we get to our colon. So now it looks right. So we have the beginning of our line, that initial space, the first group that we captured. We're using lazy capture so that it only captures as much as we need to satisfy the constraints in this captured group. Then we have spaces, colon, then we're going to have another space, which will contain one or more values, and then our second group we're going to capture is the actual value of the property that we're looking at. So this will include numbers, both positive and negative, as well as the exponent sign, positive sign, and that looks like all I need. So we're going to want one or more of those values, and that'll be our captured groups. In class, we also captured the units, so the way you would do that is you would have a third group being captured, which would include letters, a division sign, and the multiplication sign. However, for the purposes of this homework, we only actually used these first two groups, so I'm just going to leave it at that. And to get to the end of the line, we'll have a space, and then this basically we're going to say we're going to go all the way to the end of the line and capture, well, and not capture anything except a new line marker. So we use the caret to say anything except a new line, 0 or more of those, and then we use the $ to specify we got to the end of the line. And that seemed to do the trick. So we'll just make sure that we got all of our values. And yeah, this regional expression looks good. It looks like we've captured the pattern that we want to look at. So we'll then take this pattern and copy and paste it here. So now we want this pattern, we're going to want to go through the file that we downloaded and find where the text in our downloaded file matches this pattern that we've created. So we'll create this single props pattern. So this will be our regional expression that we compiled. This is going to be a raw string. So we want to put the R in front of our raw string to show that all of these slashes and characters are part of the pattern that we're looking at. They don't actually mean anything besides that. And we did this regional expression using this multi-line regional expression flags, which that just means that we're treating this text file as a series of one lines, and we're specifying the beginning of the end and the end of these lines with the caret and $. So once we have that pattern, we're now going to want to iterate through our data file in order to find what parts of our text file match this pattern. So we'll create this single props dictionary, which we'll use which a dictionary is basically just putting data from Python into pairs of keys and values. So we're going to have our single props pattern, and we want to find all of the data within our, we're going to want to find all of the data in our text file that matches this pattern. Okay, so now we've created a dictionary where the first term is the title of our property and the second term is the actual value of the property. The only issue with this is that we're using the full names of each of these properties, and we may want to use an abbreviated name for this. So to do that, I'm going to use this extract single properties dictionary, which gives the abbreviated names for each of these property values. So now we'll want to iterate through our single props dictionary and create a new dictionary that pairs the abbreviated name for each of these properties with the value that we got from our extracted data. So first we'll want to create a new dictionary where we're going to put these abbreviated names and values. Then we'll want to go through our single props dictionary. So for the key and value in each of our, for each key and value in our extract for props dictionary. So for all of the items in this dictionary. For each of the values, so the props value. So for each V in this case is representing the values in our extract single props dictionary. So that's the abbreviated name. So for each of these abbreviated names in props, the key in the props dictionary will be the abbreviated property name. And we want this to be equal to the value from our single props dictionary. To pull out the values, we're going to use what is the key in the extract single props dictionary is the key in the extract single props dictionary is going to be, well, let me write it. So this is saying our key in our props dictionary is the value from our extract single props dictionary. So props V is for each of these abbreviated terms. We have our single props key. The key in the extract single props dictionary is these full titles for our properties. So for each single props K, this will be, for example, single props molecular weight, and that will give the value of molecular weight. And so we're now putting that into this dictionary, this props dictionary, which is going to associate those values with an abbreviated name for our material property. And specified here because we don't want these values to be expressed as strings, we want them to be expressed as numbers, so we use this float function. So now we print props. We now have this dictionary with the abbreviated names for each material property and the value for each material property. And finally, we're going to use that .map class that we downloaded earlier in order to make it easier to type out the properties we want, because right now, if we type props, we'll have to write, for example, TC in here, and this will give us the value that we want. But that might be too cumbersome to type, so we will use the .map command or the .map class to make it easier. So now instead of putting what we want in brackets, we can now use this dot to, for example, if we want the critical temperature. There we go. So this is how we use regular expressions to extract a single property for a material using this pattern that we created. Okay, so now that we've created a regular expression for recognizing and extracting our single properties data, we're now going to want to make a new regular expression which will create a pattern for recognizing our material properties that aren't just a single static value, but rather a set of coefficients that we'll then put into an equation to calculate our material properties. So if we go into Regex 101 again, so now instead of wanting a pattern that will recognize these properties, we're going to want a pattern that will recognize our properties like liquid density, solid density, all of these that have a set of coefficient values that we're going to want to extract. So the first thing we're going to want to change is that we want to be in single line regex flags rather than multi-line. The difference is that multi-line will treat our pattern as several single lines, whereas this single line will mean that we'll use a dot to match when we have a new line in our pattern. So the way that will come into play is after we specify our first group. So our first group is going to be the title of our material properties. So this will include upper and lowercase letters and also spaces. And we'll want to do one or more values of these. Between our the actual title of our material property is we have this on our line, not only the material property itself, but we also have the equation number here specified. So we're going to take advantage of that in order to prevent the pattern from grabbing these single properties, because you can see the single properties don't have that equation number in the first line. So what we'll do is after we get the title of our material property, we'll have space. We wanted to do a lazy capture up until the word equation. And then because there's not just spaces in between our title and our equation, there's also stuff like the parentheses, letters, numbers. We're going to simplify this by just saying we want to basically capture anything that's not going to a new line, since that equation term is in the same line as our title. So we'll use the char to specify anything but a new line will be captured. So that will capture all of these kilomoles per cubic meter. It'll capture all our parentheses, anything before we get to that equation term. So now what's happened is that because we're including this equation term in our pattern, we're no longer capturing all of these other proper single component properties that we didn't want. So now between our title for our properties and the actual coefficient values, we have multiple lines that we don't actually want to capture. So this is where that dot, that single line regex flag comes in. So now what we're going to do is basically this dot specifies that we're going to capture any characters after our equation term. The only issue with this is that we're using a greedy capture, so we'll want to change that to lazy capture, and we only want it to go until we get to this coefs term. So now what we've done is we've captured our title only for the lines where there's this equation term in the same line, and then we're not going to capture anything until after the coefs. And actually we'll want to include the colon in those two spaces as well, because we don't want to capture those either. And then now we can finally specify our second group, which is all of these coefficients. So that will include positive and negative numbers, 0 to 9, will include decimal points, exponents, positive and negative, and I think that's it. So, and we want to do this for greedy capture, also includes spaces. And yeah, everything except for this vapor viscosity for some reason didn't get captured. Okay, so the issue was that some of these coefficient terms have 2 spaces in front of them, and some of them just have 1. So I'll just do 1 space, and then we'll have to get rid of that extra space later. So now all of our terms have been captured. So now we can add this regular expression to our Python code. Okay, so now we're wanting to create a new pattern based on this new regular expression that we've made. So we'll do a pattern, and gonna compile our regional expression. All data. And the only difference here is that we're going to use this .all, which again, that to differentiate between multi-line and .all regional expressions. With the multi-line, we're treating the pattern as multiple lines that where the beginning and end of the lines were specified by this caret and the $sign, whereas with .all, we're using this dot to match the new lines for each of our patterns. So here we have 1 line of text is 1 line in the pattern, where here we could potentially have multiple lines of text or 1 string in our pattern. And so that's accounting for those multiple lines of text that we're not going to capture in this pattern. So now that we've made our regular expression, we're going to want to, just as we did before, go through our data or our text file and find where the values in the text file match up with our pattern, and then put that into a dictionary. So we'll create a dictionary called co-op strings names, and this to be a dictionary that includes all the values from our all the values from our text file that match the pattern. Okay, so now we have a dictionary where we have the full name of our property name and then a string with our coefficients. So now that we have our values for our coefficients in a dictionary, we're going to want to do 2 things. First, we're going to want to split up the string that's going to be created with all of our coefficient values into individual coefficients, and then we're going to want to label each of those coefficients with the property that we're looking at and then the name of the coefficient. So coefficient A, B, C, etc. for whatever material property that we're looking at. So first, to get the abbreviated names, we need to go in here, get our abbreviated property names. And so what we're first going to want to do is iterate through this extract coefficient properties dictionary. So for each abbreviated name and full name in extract. So for each of the items in this dictionary, we're going to have the actual values, coefficients, will be equal to, well, okay, so we have a string with all of our coefficient values in the string. To get the coefficient values, we need to split that string up so that everything that's separated by a space gets split up into individual coefficient values. So to do that, we're going to use the split function for splitting up a regional expression. So anything that's separated by a space is going to be split up, and we're doing this for our coefficient names pad or coefficient string names. Basically what this line is saying, so for each full name coefficient string, so for example, for the string associated, all the coefficients in a string associated with, for example, the vapor pressure, well, those coefficients will now be split up based on whatever values have a space in between them. So once we have those values split up, we'll then want to give each of them their own name. So for example, if we were looking at all the coefficients for vapor pressure, we originally had that string with all the vapor pressure coefficients. We've now split those up into individual coefficient values. And now we'll want to name those based on the property they're associated with. So there'll be a coefficient that's P vaporization A, P vaporization B, P vaporization B, P vaporization C, and so on. So we're going to make another for loop, and in this for loop we're going to have for each letter and coefficient in, and now what we're going to do is we're going to use this zip function, which zip basically combines two lists. So if our first list is string dot ACI uppercase. So our first list is our letters A, B, C, etc. that we're going to use for our coefficients. And then the second list will be our coefficient values. So for each letter and coefficient in this list, if we're putting this into our props dictionary, our abbreviated name, so for example pvape, and then the letter, so for example pvape A will be our key in our props dictionary. That'll be equal to our coefficient value. So for example pvap A will be equal to whatever the value of that coefficient is. And we want that to be expressed as a float rather than a string. So let's see if that works. Oh, I think I see what the issue is that there's more than one space between each of these coefficient values. So I need to do, instead of just /s, I need to do one or more. Okay, I found what it is, so comparing with my earlier draft, should have had, okay, so the full name, a breed name, I had it flipped. So it should be, or instead of a breed name, full name, I should have full name, a breed name. Because it's for each full name in here, yeah. So for each full name in extract, I want this first term. So I want the key in extract coefficients props, not the value, because when I'm putting full name into coefficient string names, I want this full name for the value, not the abbreviated name. So that should work now. Okay, there's a discrepancy here because of that space I have after coefficients, which is causing some of these values, the coefficient is the first term, and some of these it's the second term. So I'm going to eliminate that space just to be consistent. So yeah, now all of my values are the second term. So now when I'm doing this for loop, I'm going to want to start with the first term in my coefficients list. Fix that. Okay, cool. So now we're getting okay, yeah. So here we have our props dictionary. We have up here all of our single property values, and then down here we have our coefficient values. So we can see we've combined that abbreviated name and the letter, and then we have our coefficient value, which we've converted into a float. Okay, so now that we have our regular expression for both our single property components and also for our coefficients, and we put both of those regional expressions into this props dictionary, we can now use that dictionary to calculate either the single components like we did before. So if we did props.tb, for example, we can just get one component without having to do any further calculations. Or we can use these coefficients and plug them into a function, which we'll need to define. So for example, if we want to use the coefficients that we extracted from this text file to calculate the vapor pressure of a material, we'll need to define a function for vapor pressure at a certain temperature. And we're going to use the equation from this ChemCAD list of equations. So we're using equation 101 for vapor pressure. So we'll return the exponent of our abbreviated term was P vaporization. We have our first coefficient is P vape A. Oh, and we're going to do props dot P vape A to get that value from our dictionary. vapor C. I'm not sure if I could use an umpire. Okay, so there is our expression, or there's our function for vapor pressure. So now if we want to do vapor pressure, and again, right now we're looking at the file for water. So if we want the vapor pressure of water at 273 K. Oh. Okay, does that seem right? Yeah. So there's our vapor pressure for water, which we got from our extracted data, which we put into a function for vapor pressure. We could do the same thing for heat of vaporization if we wanted another example. This one, heat of vaporization at a certain temperature. Using our list of equations, this was equation 106. So first we need to specify the critical temperature, or we also need to specify the reduced temperature, which is the temperature over the critical temperature. And then we will return this coefficient times 1 minus TR. Okay. So that gives our function for heat of vaporization. So now we want to define the heat of vaporization of water at 273 degrees Kelvin. We can get that. So these are two examples that show how we can calculate the properties of a material at a certain temperature using these extracted coefficient values. If we wanted, we could easily change the material that we were looking at. So for example, if we wanted to look at the properties of methanol, come run this again, gives critical temperature methanol, and we can now calculate the vapor pressure and heat vaporization of methanol at 273 degrees. So to summarize, we used two regular expressions to find a pattern for first the single component material properties of whatever material we downloaded into Python. Then we used our single component properties to get the whatever property we wanted, whether that was molecular weight, critical temperature, etc. Or we used the coefficients that we extracted from our text file using our second regional expression to get the coefficients that we could then put into a function for getting the calculated properties of this material. So the bigger implications of these regional expressions is that we can use them to handle really large files where we have a lot of text that we don't necessarily need everything that's there. So we can use the regional expression to quickly search for the data we want in a file and pull it out so that we can use it in a meaningful way.